page, it says page 492, chapter 13, nuclear magnetic resonance spectroscopy. And it's got a compound B and a compound C in it. It says C4H8O2. Both of those compounds have that same molecular formula. Is that what you're seeing? Can someone confirm that you're seeing what I think you're seeing?
Yeah, I can see it.
Okay, and you confronted with an NMR problem. And I don't think I mentioned calculation of degree of unsaturation in any of the videos. So what exactly is a degree of unsaturation? A degree of unsaturation can be either a pi bond or a ring. It's basically a loss of 2 hydrogens versus the saturated compound. A saturated hydrocarbon, right, saturated, has the formula CnH2n plus 2, and that's the maximum number of hydrogen atoms you can attach. So if we took a C3 compound like that, propane, we would be able to put 3 hydrogens on each of the end carbons, and we would be able to put 2 hydrogens on the center carbon, so it's C3H8, right, equals 2 times 3 plus 2. So that's a saturated hydrocarbon. If I introduce a double bond, I take away 2 hydrogens, 1 on each of the carbons that's part of the double bond. So propene is C3H6. Cyclohexane, right? Cyclohexane is just a ring of CH2s. So by forming the ring, I basically take a hydrogen off each of the 2 ends. So cyclohexane is C6H12 rather than C6H14 because it's missing 2 hydrogens. So when we calculate the degree of unsaturation, what we're looking for is how many hydrogens are missing. And for each pair of missing hydrogens equals 1 degree of unsaturation. All right, so in this case, there's 2 hydrogens missing, 1 degree of unsaturation. In this case, 2 hydrogens missing, 1 degree of unsaturation. This one has 0 degrees of unsaturation. So why do we care about the degrees of unsaturation? Well, each pair of missing hydrogens that's 1 degree of unsaturation represents either a pi bond or a ring. So by calculating the degree of unsaturation, we can determine how many pi bonds and rings we're going to be looking for. So if we look at C4H8O2, what we want to do is ask the question, what if it were saturated? How many hydrogens should there be for a C4 molecule if it were saturated? And I'm waiting for a response.
10.
So 10, right? C4H 2 times 4 plus 2 equals 10. How many are there? Right?
8.
So how many are missing?
2.
And that tells us that this molecule has 1 degree of unsaturation. So we're looking for maybe a carbonyl, maybe a carbon-carbon pi bond, or maybe a ring. But we know their saturation. And we know there can't be a benzene ring because that actually requires 4. Right? So if we don't have 2 degrees of unsaturation, we can't have an alkyne. If we don't have at least 4 degrees of unsaturation, we can't have a benzene ring. In practice, the small molecules you're going to be working with in this class, if you do have 4 degrees of unsaturation or more, there's almost certainly a benzene ring. That's the only reasonable way to get 4 degrees of unsaturation. Probably, not probably. And when I say a benzene ring, I'm talking about an aromatic, right? Aromatic compound. So we know that these C4H8O2 molecules have a degree of unsaturation. Now we have to determine what kind of degree of unsaturation that's most likely to be. And that's where the various things that you look for in a spectrum like this start to come into play. So what are the 3, just for review, what are the 3 pieces of information you get from each signal? Because that's what's going to be the quiz. 3 pieces of info from each signal, and then what gives you that information. And you just answered the second question. Right? Chemical shift is one of the things that gives you a piece of information, but what information does the chemical shift actually give you?
The environment around it, like the electrical environment.
Electronic is what we usually say, but yes.
Oops, sorry.
So if we look at this first molecule, right, there's 3 hydrogens here down at around 3.75. Right? There's a reason why they're down there at 3.75. Right? That chemical shift of 3.75 is telling us something. What's the second piece of information we can get? And remember that this delta is equal to the shift in hertz over the spec frequency in megahertz, which is tetramethylsilane. You'll see this peak at 0, right? This little tiny singlet here at 0. That is the internal standard, the tetra with the actual spectrum. And if you try to make them part of the spectrum, then you'll run into huge problems. What we're usually trying to do with a spectrum like this, it's like a jigsaw puzzle. We are trying to look at each peak and get as much information as we can possibly get out of each peak, write down a fragment that's consistent with that peak, and then at the end we try to put those fragments together. There are usually more carbons and hydrogens and sometimes oxygens in the fragments than there are in the molecule. So that allows us to piece it together by identifying which carbons must be the same carbon. Sometimes not. Sometimes the number of carbons, hydrogens, and oxygens in the fragments are identical to the molecular formula, but often not. Back in. So if you have a low bandwidth, you're probably having some issues. So what does this tell us? That there's a 3 hydrogen integration. What's
3 magnetically equivalent hydrogens
right?
there?
So there's 3 magnetically equivalent hydrogens. Is it likely to be because of a plane of symmetry when you have 3 hydrogens that are identical?
Like a CH3 kind of thing?
Yep. So the answer to the question I asked is no, right? It's not likely to be a plane of symmetry, because usually a plane is 2 things reflecting into each other. So when you have 3 magnetically equivalent hydrogens, that's likely to be rotational symmetry. and that's likely to be a methyl group. Anytime you have a 3 hydrogen integration, it's likely to be a methyl group. So this one down here at 3.75 is likely to be a methyl group, and the one that's at delta 1.1 ppm, that's also likely to be a methyl group because they're both 3 hydrogen integration. This one in the middle here at about 2.3-ish ppm has a 2 hydrogen integration. What's the most likely way to have a 2 hydrogen integration?
Being plane of symmetry, but it's also possible for rotational if there's like a third group on there.
Right, so 2 hydrogen integration, probably a plane of symmetry. A CH2 group, right, has a plane of symmetry where those 2 hydrogens will reflect into each other. So 2 hydrogen integrations are likely to be CH2 groups, and so are multiples of 2H. So if you have a 4 hydrogen integration, it's often 2 CH2 groups. If you have a 6 hydrogen integration, it's often a pair of methyl groups, right? That reflect into each other. So you've got plane of symmetry, right? The 2 methyl groups reflect into each other, and then within each methyl group you've got rotational symmetry, so the 3 hydrogens on the methyl group are identical to each other. So when you see a 6 hydrogen integration, it's often 2 identical CH3s. When you see 6 hydrogen integration, it could also be 3 CH2s, and often you'll be able to tell that based on where it is. So what does the fact that this is at 3.75 ppm tell us? It's between 3 and 4, and between 3 and 4 is typical of a certain functional group.
Is it an alcohol?
It can't tell you it's an alcohol, but what does tell you is that carbon, right, the one that had the 3 hydrogens, is probably attached to an oxygen. We don't know what else that oxygen's attached to, but the presence of the oxygen, those highly electronegative elements, right, the electronegativity of oxygen is what? You remember your electronegativity values? No. 3.4 for oxygen. Anybody remember chlorine? Things you'll learn to recognize when you see it. So we probably have a CH3O, right? So one of our carbons and 3 of our hydrogens are used there. Generally, I look at the ends first, and then I worry about the middle last, because the middle is typically the more complicated region of the spectrum. So what about this peak at 1.1? Right? Probably a CH3 group. Is there anything special about the 1.1? Does that tell us anything?
Just that it's an alkyl group?
But this follows Pascal's triangle, so we know those are magnetically equivalent. So what that tells us is that on the adjacent carbon, there must be 2 hydrogens, which means there's a CH2 group next to that. So we've now used 3 of the 8, used 1 of the oxygens. We could now go look for that CH2 group, right? Because that CH2 group ought to be somewhere. And we've got this peak at about 2.3. Right? That's a 2 hydrogen integration. And it's a quartet in a 1:3 to 3:1 ratio. So again, that's Pascal's triangle. It's a CH2. And what's it attached to? What does it tell us? That it's split into 4 peaks. The CH3 group. So this CH2 group here is this CH2 group there. And what you're seeing here is you're seeing an upfield triplet and a downfield quartet. That is typical of an ethyl group. That's a pattern that you'll see frequently. What about the fact that it's at about 2.3? Does that tell us something? And keep in mind that we're missing 1 carbon and 1 oxygen. Right? We haven't used those yet in our fragments. And a degree of unsaturation, because neither of the 2 fragments that we've written have a degree of unsaturation. So what's the most likely way of creating a degree of unsaturation from 1 carbon and 1 oxygen? That can mean lots of things, because 2.3 parts per million could mean it's next to an iodine. That's typically between 2 and 2.5 maybe. It could be that it's at 2.3 because it's on a triple bond. Alkynes show up in that region. But also in that region between 2 and 2.5 shows where, or hydrogens that are adjacent to a carbonyl group. So we probably have the carbonyl group, and that CH2 is probably attached to that carbonyl group. So now we're in a position that we can put the thing together, because we have a CH3O group, we have a carbonyl, and we have a ethyl. So now we put those fragments together, or methyl propanoate. It's propanoic acid, but we've substituted the hydrogen for a methyl group. So this is a singlet at about 3.75. The CH2 next to the carbonyl group split by the methyl is a quartet. That's about 2.3. And then we have this upfield triplet split by the 2. And we can come up with that fragment. So that's the kind of process that you're going to use for analyzing NMR spectra. And all that's changed versus the other structure is that the oxygen is on the other side of the carbonyl group. So it's next to the ethyl group here instead of next to the methyl group, and we have ethyl acetate. So that pattern where you see that upfield triplet and the downfield quartet, and this time the quartet is way down. If that downfield quartet is between 3 and 4 parts per million, it's almost always an ethoxy group as opposed to an ethyl group. Right? So that's a distinctive pattern, that when you see that triplet here upfield and this quartet downfield in that 3:2 ratio, you'll see, oh, there's an ethoxy group. When you see this big singlet at 2.1, you'll learn to recognize that that's probably a methyl ketone. Here we have the upfield triplet and the downfield quartet, but the quartet's not that far downfield. That's an ethyl group, but the CH2 is now attached to something else. But this big singlet between 3 and 4, that's almost always a methoxy group.